Hi, let's talk about the switching process in our synchronous buck converter. What we want to do is to validate a couple of ideas that we have introduced in previous videos. The first one is that we want to demonstrate that the switching process of MOSFET SA is similar to that of the design with the Schottky diode. And the second idea is that the turn on and the turn off process of MOSFET SV doesn't lead to a remarkable power consumption. In other words, the switching losses of MOSFET SV are negligible. Remember that we said that because we know that the switching process of MOSFET SV involves two possible current paths. One is through the MOSFET channel when the device is on, and another one is through the body diode during the dead time. So when we turn on or we turn off the MOSFET, what we do is a change in the current path, but it's always through the same switch, SV. So basically in one case the current changes from the channel to the body diode, and in another case changes from the body diode to the channel. But in both cases we said that the voltage across the switch was more or less 0 volts. So as a consequence there is no overlap between voltage and current, and as a consequence we say that the power consumption in that transition is negligible. Okay, but let's see this with the simulation. So here you have the schematic we are going to use. Is the same circuit that we have seen in the previous videos, and let's start with for instance with the turn on process of MOSFET SA. So here we are evaluating in green the voltage across the switch, and then in red we have the current through the switch evaluated in that way. So as we can see, the simulation result is very similar to the case with the Schottky diode approach. Basically what we see is that since we are turning on the MOSFET, the voltage across the device goes to 0, and at the same time the current rises from 0 to the inductor current here. And moreover, as in the case of the Schottky diode, what we see here is a current peak. Okay, this is the consequence of the reverse recovery process, but in this case is the reverse recovery of the body diode of the second MOSFET. Okay, so at the end we have some overlap, as a consequence some power consumption that we can easily evaluate with LTspice. Okay, let's see the turn off. In this case it's also very similar to the case with the Schottky diode. We turn off the main MOSFET, so the current through it falls, the voltage rises because it's going to block the input voltage, and we have some overlap between voltage and current, and as a consequence some power consumption during the turn off of this device. So in summary, the turn on process and the turn off process of MOSFET SA is very similar to the one with the Schottky diode. Okay, let's see what happens with the second MOSFET, MOSFET SV. And let's start with the turn on process. Here we have, in green we have the voltage across the second MOSFET. And in red we have the current through the second MOSFET evaluated in that way. And as a reference, I indicate that here, in that moment, we turn on the MOSFET here. I know that because I have checked the control signal. I don't include the control signal in this screenshot in order to facilitate the interpretation of the result. But it's important to take into account that we turn on the MOSFET at this point. So first of all, let me try to explain what is happening in this transition. Let's start in the first interval that we can identify. So in this part, in this interval, MOSFET SA is driving the current, because as you can see here, the current through MOSFET SV is 0. Then here we have the turn off start of the MOSFET SA. And this switching transition involves MOSFET SA and the body diode of MOSFET SV. So as you can see, the voltage across MOSFET SV falls, the current through the switch rises, but we didn't turn on the MOSFET. So this current is driven by the body diode. So let's put here that in this interval, what we have is the switching transition from MOSFET SA to the body diode of SV. Okay, SV body diode. And then in this part, we can consider that the body diode is driving all the current, because as you can see, the current through the switch is the inductor current, but we didn't turn on the MOSFET. And at the same time here, the voltage that we see here is more or less minus 0.7 volts, because basically here, as we explained in previous videos, what we see is the forward voltage drop of the body diode. So in this part, the device that is driving the current is switch SV, and in particular the body diode. And finally, here we turn on the device, we turn on the MOSFET, and all the current is flowing through this through the MOSFET channel. So an important conclusion here is that before we turn on the MOSFET, the voltage is already 0. It's not 0, it's minus 0.7, but it's close to 0. And after the turn on process is also 0. So as a consequence, during the turn on transition, there is no overlap between voltage and current. And as a consequence, if you check the instantaneous power consumption, you will see that it's negligible. Okay, let's see the same, but in this case we are talking about the turn off. So again, as a reference, here we have the moment in which we turn off the MOSFET. So let's repeat the process. Well, so here MOSFET SV was driving all the current. As you can see, this current level is close to 15 amps, which is the inductor current, and the voltage is close to 0. Then we turn off the device, we turn off the MOSFET. What is happening in this region? Well, what we know is that the MOSFET is not activated, and as a consequence, the current through the inductor must find a path, and the only possible path is the body diode of MOSFET SV. So what we know is that here the body diode is activated and it drives all the current. We can see that in the voltage, because here again we see minus 0.7 volts as in the previous case. Then we have the turn on process of the main MOSFET here. So in this part, or this interval, involves SV body diode and SA MOSFET. And finally, all the current is flowing through the main MOSFET in this interval, because as you can see, the current through the second MOSFET is 0. What is the conclusion here? If we check the turn-off process of the MOSFET in this part, what we see is that before and after the change, the voltage is almost zero. So again, there is no overlap between voltage and current during that transition, and as a consequence, the power consumption in that transition is negligible. So with this, we finish with the target of this video, and let's see you in another video. Bye.